Let's move on to distribution. We have population distribution, which apparently talks about the distribution of the whole population. We also have something called sample distribution, where actually what I want to talk about is the sampling distribution of the mean. Now here's the idea about the sampling distribution of the mean. Recall that I mentioned that when we're interested in the population, we have to take a sample, okay? We could calculate sample mean and make inference about the population mean. But now, since they are not equal, we need to build a bridge, okay? If we want to use sample mean to represent the population mean, we first of all have to know something about the sample mean. Is the sample mean we get close to the population, okay? So we benefit from large sample size. Why should we take large sample size? Now, intuitively, we all know large sample size is good for us. It can better represent the whole population. Why is that? Also, if we keep drawing samples from the same population, how would our sample means be distributed? Are they all close to the population mean? Are they scattered everywhere? So that's the questions we need to answer before using sample mean to draw inference about the population mean. So this leads to one important theorem in statistics called central limit theorem. The central limit theorem answers the questions I just asked. Okay, so the central limit theorem tells us the distribution of our sample mean. Basically, the idea is now you have a population. Typically, you would just draw one sample, use that sample to make inference about the whole population. But if you keep drawing samples from that population again and again, you're going to obtain many sample means. And I can guarantee not all sample means will be the same. Actually, they will be quite different. The sample means will be different from one sample to the next. Then you face this situation. Which sample mean is the best? Which sample mean you want to use? Do you want to average all sample means and then use the average of all the sample means, right? So the central limit theorem tells us if you keep drawing sample means from the same population of the same size, your sample mean actually follows normal distribution. I don't have it here, but I could highlight, okay? So basically, the sample mean, if you keep drawing samples from the population, all the sample mean putting together, you will find it follows normal distribution. That is, most of the sample means are close to the true population mean. That's good news. That's really good reason for us to use sample mean in the first place. Okay. In addition, we also find out that for this normal distribution, the standard error of all the sample means is equal to the population standard deviation divided by the square root of sample size. Okay, so this allows us to actually accurately picture the distribution of the sample mean. Okay, then when we use the sample mean to make further inference, we could start from there, right? So with the central limit theorem, statisticians are able to come up with a calculation for confidence interval. What is confidence interval? Here's the idea. We first start something called point, okay? So point estimate is an estimate of the population mean in the form of a single value, usually sample mean, okay? If you want to estimate the population mean, the best thing is draw a sample, get the sample mean. The sample mean is regarded as a point estimate because it's just a single value. Okay, now the problem with the single value is it gives no information about the possible magnitude of random sampling error. Apparently, if you take another sample, you get another point estimate of the population. Which one is good? Again, the old question comes up, right? Which one do you use? So the better solution is to do a confidence interval estimate, okay? So confidence interval estimate is a specified range of numbers within which a population mean is expected to lie. Okay, we would like to provide a range for the population mean. And in particular, when we produce this range, we are very confident. Actually, we want to be as confident as we could, and that's why we call it confidence interval. Okay, it's a range for the population mean. It's not an ordinary range. It's a range that we are very confident that the population mean would be within the range. Okay, the good thing about producing a confidence interval instead of using point estimate could be illustrated with my previous example about the demand, right? If you only use sample mean as the estimate and say, oh, this is average demand, I'm gonna provide inventory equal to the average demand. Guess what? You're gonna disappoint your customer almost 50% of the time, depending on, of course, the distribution of your demand, right? Then you are not running a good business. So a better way to do that is really to come up with a confidence interval. It's a range for the population mean. The population mean could be anywhere in this range, and you want to take the upper bound so that you are not missing a lot. So how do we construct confidence interval? Well, the basic structure is the following, okay? Let's just suppose we're constructing the interval, confidence interval for a population mean. Okay, we're constructing an interval for the population mean, right? To do that, we actually start with the point estimator, which is the sample mean. So we start with the point estimates, which of course is a sample mean. We need to start from somewhere, and sample mean is the best starting point. Okay, now realizing that the sample mean could be different from the population mean, it could deviate from the true population mean, we're gonna add some buffer to it. And the buffer we add is called margin of error. So we're gonna add and then subtract, so plus or minus margin of error. Margin of error. It is basically the scale times standard deviation of sample. Okay, so that's the structure of confidence interval. And let me draw something so that it is also as clear to you. In the middle, we have the sample mean. That's the starting point for us. We have to start from somewhere, so the best point is the sample mean, because at least it's relatively close to the population mean than other measures like the standard deviation or the maximum or the minimum, right? Start from this. And we realize that, again, population mean could be different. We add buffers, all right? We first add, starting from the sample mean, we're gonna add margin of error. This actually also illustrates our tolerance of error in terms of estimating the confidence interval and determining the sample size. We'll talk about that later. On the left hand, we're gonna do the same thing. We're gonna start from the sample mean, okay? And then we subtract the margin of error to find the lower bound. And this range is what we call the confidence interval, okay? Now, how do we determine the margin of error? It is calculated as a scale times standard deviation of the sample mean. Now, the scale, this number, scale, will depend on how confident we want to be, okay? When we say confidence intervals, we actually choose how confident we want to be. The most one is 99.99999%. Okay, we can never be 100% confident in the case of uncertainty. If we face uncertainty, we cannot be 100% confident. Okay, otherwise you don't need statistics. Now the most is typically we pick 99%, but the default level or the typical level is 95%, which means we have 5% tolerance for error. Sometimes we'll also pick 90%, and that is because if this is something not critical, we could relax the confidence level. But for 95% confidence level, if we want to be 95% confident, then the scale we want to use will be not 1.96. I believe if you know statistics, you must have heard this number 1.96 in terms of constructing confidence interval. Okay, and 1.96 actually comes from standard normal distribution. See, we're using standard normal distribution. We're also actually using central limit theorem because by knowing that the sample mean follows normal distribution, we'll be able to construct the confidence interval. Now, if we're changing to 99%, then we will be using a different number, and that number is roughly 2.57. So here's more discussion about confidence interval. There are a few things I would like to let you know. Now, for the confidence level, okay, the default level is 95%. If this is something critical, you would like to make that higher, for example, 99%. If this is something that's not critical, you're gonna make it 90%. As a researcher, we're gonna pick the confidence level, and the confidence level will in turn determine the sample size we need for our study. This is also because the confidence level determines the amount of error we are able to tolerate. Oh, here they are. I've listed the scale used with different confidence levels. For 95%, that's 1.96. 99%, that's 2.576. 90%, that's 1.645. Now, if we're going to calculate the confidence interval manually, we need these numbers. However, there are a lot of statistical software that will calculate the confidence interval for us. So we will be able to get the interval directly. What's more important is for us to be able to appreciate the usefulness of confidence interval and for us to be able to use it whenever we need to. One last topic in this chapter, we have been talking about choosing sample size, starting from the example we had at the beginning. So now it's time to talk about how we choose sample size. It actually comes from confidence interval construction. Based on that construction, we actually could reverse it a little bit. And if we manipulate the formula we just see right here, we could find out that the sample size is equal to z times s divided by e squared. Now here, the z, of course, is the scale we were talking about, and that depends on the confidence level, okay? The basic means how much error we are able to tolerate. S stands for the standard deviation, and this could come from the population if we have past knowledge about the standard deviation. We use that. If we don't, we usually conduct a pilot study to find out the standard deviation. The margin of error denoted by E is kind of measuring how precise we want the estimate to be, okay, or how much margin of error we could tolerate in our calculation. If I want to construct a confidence interval and I can only tolerate, for example, $2 margin of error, then E will take a value of 2, right? Here's an example. Suppose a survey researcher studying expenditures on lipstick wishes to have a 95% confidence level and a range of error of less than $2. That is, after constructing the confidence interval, the interval can only have a width of 4. Think about it. We are constructing confidence interval for the expenditure on lipsticks, right? And the range of error, which is margin of error, is less than $2. So starting from the middle, which is X bar, we can only add $2 here to the upper bound and subtract $2 here on the lower bound, okay? And therefore, the total width of the interval should be less than $4. That's how much the researcher can tolerate, right? The researcher also estimates the standard deviation of be $29. We want to find out the sample size we needed to construct the interval. So according to the formula, if you plug in all the numbers, go through the calculation, it turns to be 808. Now, when determining the sample size, apparently for this calculation, there will be decimal places, right? So 28.42 times 28.42, that gives us 807.69. When calculating sample size, we'll always round up to the next integer. It doesn't matter what decimal places we have. We always round up to the next integer. In this case, we need 808 respondents or observations. But actually, if you think about it, the number of surveys the researcher needs to sum down, it must be much higher than that, right? Because the response rate for surveys is usually low. So you need to take that into consideration as well. Now, what if we change the range of error? What if we now tolerate $4 as the range of error? That is, we can tolerate more error, but we're able to live with a wider interval. If we go through the calculation, the sample size reduces to 202 observations. That's good and bad. The good is, yes, you have less work. You are facing a smaller sample size. The bad is, actually, for confidence interval, narrow intervals are more useful than wider intervals. Now think about it. The logic is you are using interval to try to kind of pinpoint the population mean. If you have a wider range, that means the population mean could take a lot of values. Okay, I can give you a very quick example to help you to get the point. Now, for your course grade, suppose I'm teaching undergraduate course, and undergraduate students are typically very curious about what their course grade will be at the very beginning of the semester, right? And if I have a student coming to me and say, oh, statistics is my least favorite subject, I'm so scared. I need to know how well I'm going to be on this course. At the very beginning, I could say, look, I'm 100% confident that your course grade is between, guess what, 0 and 100. That's the widest range I could come up with. It's still a confidence interval. Now, that's a special case because I'm 100% confident from 0 to 100. That's the widest one I could give, and that's the useless one, right? It doesn't convey any information. I guess the student would rather want me to say, I'm 90% confident that your course grade will be between 60 and 100. At least that means he's passing the course. That's a narrow interval, right? And it is more useful. So this is why we prefer narrow interval. And even though we can decrease the sample size, we're sacrificing the width of the interval. The other thing we could change, the other parameter we could change is we could pick different confidence levels. We could pick a 99% confidence level, and apparently the z-value will be changed. Look at the calculation. If you want to be 99% confident instead of 95% confident, for the first case with $2 margin of error, we need a sample size of 1,389 observations, substantially larger. And similarly, if we can tolerate $4 as margin of error, the sample size also increases to 347 observations. So this is how we use confidence interval construction to calculate the sample size. In practice, this could be very useful. And that's all we have for this chapter, chapter 17. I will see you next time.